Okay, it is my pleasure today to introduce John Kleinberg. John is a professor at Cornell University. He works on algorithms and fairness and social networks. Algorithms and social networks is his area of specialty. He has had a lot of impact in the area, which he has contributed, he has partially created. He was the recipient of many honors, including in particular the MacArthur Fellowship, which in the US is known colloquially as the Genius Award. Welcome, John.
Thank you. Okay, thank you very much for the opportunity to speak here. What I wanted to do today was talk about algorithms and fairness. And this is a topic that there's been a growing amount of concern about as people see algorithms being applied in more and more situations, more and more consequential policy sorts of domains. And the question is, if we recognize the sorts of bias, discrimination, and unfairness that exists in the world, will the use of algorithms simply incorporate that bias and reflect it in these new automated settings? Is it possible it could even increase the amount of bias? Or if we design them correctly, could it reduce the amount of bias? And these are all questions that people are actively debating. And there's an opportunity here, if we can think about it at a mathematical and formal level, to try understanding whether there are ways that we can design algorithms to make them more or less fair. Now, in order to ask these questions, it's useful to walk through some examples where algorithms are being used to make these kinds of predictions. Fundamentally, what we're talking about is a situation where an algorithm takes somebody, determines some set of features about them, and then tries to make a prediction of their future behavior. Where do we see this? Well, we see this a lot on the internet. So for example, next week's lecturer, Tim Roughgarden, has a new book about algorithms. So if you were to want to look at this book before next week's lecture, you might go to Amazon.com, some online retailer, and try to purchase the book. Now, I'm less interested in exactly what goes on when Amazon tries to sell you the book, and more about a particular prediction that it makes, which is if you have a profile on Amazon, if you've bought lots of books there, it has some sense of what kinds of things you're interested in just based on your past history. And so it might make some recommendations. It might say, given that you're looking at this book, given what else you've been interested in, we predict that you're going to also be interested in these things. And this is, on the internet, a simple example that we encounter every day of this kind of process I'm talking about, where we take a person with a complex range of behaviors. When you read books, you have lots of interests, you know lots of things. But to Amazon, it only sees this very thin segment of your behavior. It sees what it was that you've purchased on Amazon, and it makes a prediction about what you're likely to do in the future. And we see this on the internet a lot. If you're signed in to Google, for example, then when you search on Google, you're not just seeing its generic results, you're seeing results that to some extent take into account features based on your past behavior. When you sign into a social media site like Facebook, in your news feed, you're seeing things that are tailored to your interests and your past behavior. All of these cases where it's taking some very rich, real-world individual and boiling down the situation to some small set of features. Now, I think where people are beginning to see that this is an even more serious concern to think about is that we're beginning to see the same paradigm applied in situations that we think of as the offline world. So here is a situation that superficially looks very different, but is, I would argue, really the same kind of situation. When you apply for a job, and we were just hearing about job applications, and I'll also use that as an example in my lecture, although in a different context from Professor Mathieu. You apply for a job, you submit a resume, for example. You submit maybe a college transcript. You submit various pieces of information about yourself. And in a way, this is actually doing something very similar to what was happening on the back end of Amazon, which is you've had some rich, large range of life experiences. But when you go to apply for the job, obviously the person evaluating your application can't really know all of those experiences. They have to communicate with you through this relatively thin communication channel, which reduces that to some list of bullets on a resume, some list of courses on a college transcript, and so forth. And in the process, they're going to make a decision about hiring you. Now, this is already something we could worry about when human beings are making this determination from something like a resume or a CV. But it's a domain where we're now starting to see algorithms assisting. Algorithms will take some of this data, we'll look at how past applicants did in this job, and we'll try to make a prediction. How will this applicant with this data that we know about them do in this new job description? Okay? Again, the algorithm here is helping. It's not necessarily making the decision. It's simply providing an estimate of the probability that this person will succeed in this job. And again, it could make the situation better or it could make the situation worse relative to the human decision maker. It's clear that humans in hiring situations make lots of mistakes, make lots of bad judgments. There's certainly room for improvement. It's a separate question whether the algorithm could actually improve. We could talk about this in a number of different domains. We could do this with college applications. This is the first page. If you want to apply to the university which I work at, Cornell University, you would start here. You would enter a lot of data about yourself, and it would begin trying to make a decision, the admissions process about whether to admit you. Okay, so all of these have the following basic pattern, which is what I wanted to start from, right? Across online content like Amazon or Google or Facebook, across hiring, across admissions to education, all of them, in some sense, follow this abstract pipeline. That here we have some individual. Let's see, there's a laser. There it is. Yeah. We have some individual. Neither the algorithmic process, nor for that matter the bureaucratic human process, can actually truly understand the individual. And so from the individual, we determine some set of features that we're going to look at, that we're going to use for this evaluation. We then pass that into either an algorithm or some human administrative process, takes the features and tries to make some kind of a prediction about their future behavior. Will they be interested in this book? Will they succeed in this job? Will they succeed in this college that we're admitting them to? We're not actually thinking about necessarily the final decision. We're only going to get up to the point where this process is making a prediction, high probability or low probability. And there are a number of questions that people are beginning to ask as algorithms get deployed for these kinds of situations. One that we could ask is at this end of the process, which is the algorithm really focusing on the right outcome? So for example, in a hiring context, I've asserted that what we should be interested in is, will this person succeed at the given job description? But maybe that's too simplistic a question. Maybe we should ask, will this person work well with the team of employees who's already working for the company? That would be a slightly different refinement of the question. And so even figuring out what is the outcome that we should be predicting can be complicated. Certainly on the left-hand side, the question, have we mapped individuals to features, is also a very complicated question. Maybe there are things about the person that we could have recorded that would have given us a lot of additional information, allowed us to make better predictions. These two are sort of implicit in the third question, which I want to spend most of my time talking about today, which is, are the algorithm's decisions fair in some sense? If we look at all the people who are being evaluated, is it making fair decisions? Now, obviously, the first big challenge for us is to try addressing what we might mean by the word fair. And it's unlikely, considering what a complex concept this is, that in the course of one lecture I'm going to give a complete, comprehensive definition of the word fair. But I want to start talking about some of the aspects where we can operationalize that definition in certain ways to actually analyze some of the algorithms which are being used in some of these contexts. Now, the situation where this came up in our research, we had been looking at a number of domains like this, and certainly looking at online commerce, online social media, looking at at things like employment and admissions. But the particular case where we encountered this question most concretely over the past 2 years was actually in a domain which is even more consequential in a sense than these, and to some extent more controversial as well. And that is the use of algorithms in the criminal justice system. So this is a domain where over the past few years, people have been exploring the use of automated risk tools to help judges in making decisions. A particular place where people have looked at this, for example, is in assigning bail to criminal defendants. So someone is arrested, and I'll describe the process in the US, although in a number of jurisdictions it's relatively similar. The person is brought before a judge, and the question is, will they wait for trial in jail, or will they be released pending the scheduling of their trial? And it's societally desirable that if this person is not going to pose a risk to public safety, then they shouldn't have to wait in jail for their trial. And so the law asks the judge to make a prediction. The law says the bail hearing is not about deciding guilt or innocence or the severity of the crime or the incentive effects of this decision on other defendants' behavior. The bail hearing is about predicting whether this person will return for their court appearance without committing a crime in the meantime. And if you believe that they will, then you should grant bail and release them, and they don't have to wait for trial in jail. So this is an interesting point in the long pipeline of decisions that get made in the criminal justice system. Bail, arrest, bail, trial, sentencing, parole, all of those. Bail is the one that's closest to a pure prediction problem. And it's known that judges obviously are not perfect at making this prediction. Sometimes they release people who go on to commit a crime. Sometimes they jail people who almost surely would not have committed a crime had they been released. And so it's plausible to say there may be room to help judges make better decisions. How might we do that? Well, one proposal has been algorithms that certainly won't make the decisions themselves, but will provide estimates of probability, estimates of risk. They can look at features about the defendant and say, the algorithm thinks this person is higher risk or lower risk. Okay, that's the idea. Now, I say this is consequential, obviously, because an important branch point in somebody's life is being determined by what this algorithm provides to the judge. And it's also controversial, since it feels in many ways dangerous to be giving this much power to an algorithm. Yet at the same time, we know judges are making mistakes. We would like to find tools that can help them. Okay, so there were a number of tools that are being used for this. Roughly a year and a half ago, in summer of 2016, a very active public debate which began to bring in people from the technology world, from law, from government and policy, sprang up around this particular tool called Compass. And it was all triggered by a report by the investigative journalism organization ProPublica, which wrote a report based on extensive analysis of some public domain records from Compass with the title Machine Bias, with the tagline, there's software used around the country to predict future criminals, and it's biased against black defendants. Why were they saying this? Well, what they had done was taken the results of the analysis that this tool called Compass was doing. They took the same features that Compass had in a particular county in Florida, Broward County, and they looked at the scores it was assigning, and then they looked at what actually happened to these defendants when they were subsequently released, and asked how was the tool actually doing. And they found a number of things, but the crux of their concern could be boiled down to the following pair of facts. The first fact is they looked at defendants who, after they were released, did not actually go on to commit a future crime. And they looked at the risk that had been assigned to each of them, the estimated risk that the algorithm had given to them. And they found that African Americans who didn't subsequently commit a future crime had been given higher average risk scores than white defendants who didn't reoffend. right? So in this context, a high score is a bad thing for a defendant, right? This means you're being viewed as very risky. And so in this first bullet, we had a set of people, none of whom actually went on to do anything wrong, and yet the algorithm had systematically given higher average scores to the African-American defendants. And there's something that's somehow facially unfair about that, if you think that these two groups, in this case, neither of whom committed a future crime, got different scores. And the converse thing was happening for people who did go on to commit future crimes. If you look at white defendants who went on to commit future crimes, they had lower scores on average than African Americans who went on to commit future crimes, something which correspondingly feels inherently unfair. So this was a topic that we had been thinking about. This was an extremely concrete concern that had been raised about one of the widely used tools here. We wanted to think more about where might this be coming from? Why might this be happening? Okay. So it won't be surprising to hear that the people behind the Compass risk tool, which was a firm called Northpoint, defended what they were doing rather forcefully after this report came out. And they were actually helped in this defense by a number of researchers in the crime policy field who pointed out that despite this objection, Compass had been designed with a particular guarantee in mind that was clearly something desirable. So what was the guarantee that Compass actually was trying to satisfy? Well, it was this alternate definition, which in a sense is also a kind of definition of fairness. The definition is called calibration, and I wanted to say a bit about what calibration is. So remember, what a risk tool is doing is assigning a score to each defendant, which is an estimate of the probability that they will commit a crime in the future, or at least be arrested for a crime in the future, which of course is important to notice is a different thing. Here's what they pointed out. They said, let's look at all African Americans who are assigned some score of S. Okay, so here, for example, I have a lot of defendants, and we've grouped them. These are all the ones who got assigned a score of 0.1, 0.2, 0.4, 0.6, for example. So all the ones assigned a score of S like 0.1. What you find if you look at the data is that an S fraction of them actually go on to reoffend. Right? So if red here means someone who went on to commit a crime in the future, then in this set labeled 0.1, 1 out of 10 commit a crime. In this set labeled 0.2, 2 out of 10 commit a crime. 0.4, 2 out of 5, or 40% go on to commit a crime. In other words, this number S, the score, means what it says it means. It was intended to be a probability that a future crime is committed. And sure enough, if you look at the set of all people with a given label, that fraction of them went on to commit a crime in the future. And crucially, this was true both of African American defendants, where a score of S meant S, and for white defendants, where again a score of S meant S. Okay? It meant the same thing in both cases. And so the people behind Compass said, this is the sense in which the tool is fair. It is race blind. S means S, regardless of the race of the defendant. That is all anyone ever asked for when we were creating these probability estimates. Right? What we should be asking is that when we assign someone a score of S, it means there is a probability of S, even if you look at the historical data, that they commit a crime. And that's true regardless of race. So that too seems like an important thing to have. And in fact, it would be a big problem, in a sense, if you did not have a tool that was calibrated, if the score of S did not mean S across each group. What's an example of a problem that you might have if you had an uncalibrated tool? Let me give you an example from back in one of our previous domains, say hiring. Suppose we were doing hiring with a tool that predicted your probability, we were hiring doctors, say, and we're trying to predict your probability of being a good doctor. So now a high score is a good thing. It means you are likely to be an excellent doctor. Suppose that in our little example here, hospitals were to hire doctors using a score that was not calibrated with respect to gender. In other words, the scores meant two different things for the two different genders of doctors. And suppose hospitals went into the group with the highest score and they just hired all of those doctors. What would a failure of calibration mean? Failure of calibration means something like the following, that female doctors with a score of S star, the highest score, are more likely to be good doctors than male doctors with the same score, S star. Right? That's what it would mean for this score not to mean the same thing for the two groups, in this case, gender of doctors. Well, the problem is if hospitals are hiring using a rule that has this property, then when you're a patient trying to select a doctor, it would actually be rational to select your doctor, at least in part, based on their gender. In a sense, the rule is actually telling you to do that. It's telling you the female doctors we hire are on average better than the male doctors we hire because the rule wasn't calibrated with respect to gender. That seems like a bad thing. Right? There seems to be, it's encouraging unfair behavior on the part of the population. Okay, let's go back to criminal risk scores. So we have calibration, which seems important, but ProPublica's objections are still there, that if you look at people who didn't go on to commit any future crime, African Americans had a higher average score than white defendants, which seems inherently unfair. So could we have all the desired properties at once, right? Could we achieve calibration, but also achieve this property that the averages are equal? And this is something I think that's sort of common when we think about algorithms, that there's sort of one's first impulse in a situation where you see an opportunity to design an algorithm is you plunge ahead and you do something, and you write something, and you try it out, and you say it does this and this and this and this. But then it sometimes helps to step back and say, let's pause. Let's ask, what is it you were trying to achieve? Rather than talk about what it, exactly how your algorithm works or what it's doing, let's talk about the properties that you would like to satisfy with this algorithm. And let's reason about how they can be achieved. Okay, and then we'll go back to our algorithm thinking in terms of these properties that we wanted. So here we've written down some properties that we want. We'd like calibration. We'd like these average scores to be equal, looking retrospectively at what people did. How would we go about achieving them? And what we found, actually, was that by simply trying to define all of these things carefully, we were able to somewhat disentangle this debate that was going on about this tool. OK, so first, let's take the story I've been telling so far and state it just slightly more formally as a model. So what are the ingredients that we've had so far that we want to put in our model? So first of all, we have individuals. Individuals have two salient properties. One is they're either positive or negative for the behavior that we're interested in. So let's think about the criminal justice example. A positive instance, that's bad. That means they go on to commit a future crime. A negative instance, in this case, is good. They don't go on to commit a future crime. The other salient feature about individuals is they belong to one of two groups, A or B. Say white defendants or African American defendants. Say male doctors or female doctors in our hiring example where we're concerned about fairness with respect to gender. Okay, so they're either positive or negative. They either belong to group A or B. We have this pipeline. The individual, we determine some features, a set of features using the data we have access to. And then we assign each individual to some category here, which I'll call a bin, just based on how I drew them. And each bin B has a score V sub B, which is the probability that they're going to be in the positive class. Right? So that was like the 0.1, 0.2, and so forth. That's the entire model. And the desired properties, we can now say, are these three that we've talked about already. One is calibration within groups. For each group, A and B, a V sub B fraction of the people in bin B are actually positive. In other words, we gave this bin the correct score. VB really means the probability. And for both groups. Second, what I'll call balance. This was the equal averages condition. Balance for the positive class means that the average score of the positive members in group A should equal the average score of the positive members in group B. And similarly, I want balance for the negative class. Right? Average score of negative members in group A equals the average score of negative members in group B. That last one is, for example, among people who did not commit a crime, the average risk score assigned to defendants in group A should be the same as the average assigned to defendants in group B. OK. Good. So let's ask the question, can we have all these properties? All three of these are desirable properties. All three seem to correspond to some notion of fairness. Can we achieve them all? Well, the first thing I'd like to notice is sometimes we can achieve them all. there are at least two simple cases where we could achieve all of these properties. One is if we have what I'll call perfect prediction. So perfect prediction means that for any given set of features, once you tell me the features, I know with probability either 0 or 1 that the person will commit a future crime. In that case, I can simply assign a score of 0 or 1 to each person. And while we'd have to actually check, we can check that, in fact, we satisfy all of the properties. So if I can predict perfectly from the features you give me, then we can do that. A second, slightly less extreme case where we can achieve these three properties is if what we have what I'll call equal base rates. If I look at the two groups, and the two groups have the same fraction of positive instances. In other words, say for white defendants and African American defendants, the same fraction go on to commit a crime in the future. Then we could at least have a very trivial risk score that satisfies all three properties, which would be, suppose that base rate is 0.3. There's a 0.3 probability that white defendants will commit a future crime, and there's a 0.3 probability that African American defendants will commit a crime. I could just assign everybody a score of 0.3. It would not be very informative for the judge. It wouldn't be very helpful. But it would at least satisfy the three properties. It would be calibrated. 0.3 means 0.3. And it would have the same averages for everybody. Okay? So not very useful, but at least we've pinned down a second case where we could. Okay, so two very simple situations in which we can achieve all three properties. Now, here's the surprising follow-up to that, though. And this is a theorem from some joint work with Senthil Mullainathan and Manish Raghavan, that in any instance of risk score assignment where all three properties can be achieved, we must be in one of those two cases. In every other situation, it's actually impossible to achieve all three of these properties. And so, in fact, what was going on in this ferocious debate that was taking place over what conditions the compass risk tool should satisfy, should it have equal averages? Should it be calibrated? In a sense, the debate was over things that could not be achieved simultaneously, right? That it was simply mathematically impossible to resolve the dispute that was going on because the kind of fairness that one side wanted was incompatible with the kind of fairness that the other side wanted. You had to actually make a choice. They were all reasonable definitions. In general, you could not have them all. There's some notes I should make here. One is, in the end, this is not actually really a theorem about algorithms per se. It's not about limits on computational power. It's really a theorem about the specification of what we wanted, right? It's simply a limitation on assigning estimates that actually equalize all these. And so as such, it would also apply to human beings making this decision. If I have a human process that's assigning risk scores to people, it too will be faced with this inherent trade-off between calibration and balance, equalized averages. Okay, I wanted to say a couple things. So we actually we were able to kind of jump into this debate a little bit. ProPublica wrote a follow-up to say that bias is mathematically inevitable, which is not necessarily exactly how we would have phrased it, but fundamentally gets at the fact that there are these inherent trade-offs between different definitions. And there were a number of concurrent and subsequent lines of work that we and others investigated, which I won't really try to summarize except to point out this interesting work of Martz, Hart, Eric Price, and Nati Shrebro, which looked at what would happen if you took away calibration. They said that was the one they felt was the most reasonable to take away, and looked at the optimization problem of how should we design classification algorithms if our goal is to equalize the averages. And that's generated a number of interesting pieces of work on how to do that. Okay, but I want to talk for 2 slides about this theorem and just give you a sketch of how to prove it. Because in the end, I think one thing that we took away from it is once you actually write down the definitions carefully, in some sense, the hard part is behind you, and it's just a question. the actual proof is not that complicated. Something I can at least summarize for you in the next 2 slides. Okay, so here's why there's this inherent tension between calibration and equalizing averages. And so just a short sketch. So we have these 2 groups. So let's say n sub t is the number of people in group T. And let's say that of those n sub t people, k sub t that's the expected number of people who are going to be in the positive class, who are going to commit a crime. Okay? Now, so, right, maybe the groups are A and B, so n sub A and n sub B. Okay, now the calibration condition, what we're going to think about in the proof is to look at everyone's assigned a score, a probability they're going to commit a future crime. So we can think about all the score that's handed out to all the people, and we're going to think about the total score that gets handed out. And we're going to try to count that total score in different ways and try to conclude something from that. So what do I mean by counting the total score in different ways? Well, if this bin here is calibrated, then everybody, all 10 people there get assigned a score of 0.1, and 1 person goes on to commit a crime. In the second bin, all 10 people get assigned a score of 0.2, and 2 people go on to commit a crime. In other words, calibration implies the total score of all people in a given bin is equal to the expected number of people in that bin who go on to commit a crime. Those 2 numbers are equal. Total score, expected number of crimes. If I now sum over all bins, what I find is that the total score handed out to all of group T is equal to the expected number of group T people who go on to commit a crime, who are in the positive class. Okay, so summarize that here. NT is the number of people in group T, KT is the number of people in the positive class, and by calibration, it's also the total score assigned. Okay, that's one way. So one way to count the total score is just to say, by calibration, it's KT. Now let's think about the equal averages condition and try to count the total score a different way. To do that, let's say X is the average score of a person in the negative class. So that's a low number, hopefully, corresponding to people who don't go on to commit a crime. Let Y be the average score of a person in the positive class. That's a presumably higher score corresponding to people who do go on to commit a crime. Now, equalized averages says X and Y are independent of the group T we're talking about, right? This is not X sub T. This is just X, because it should be the same average for every group. That's the whole point of the balance fairness condition. So that means the total score in group T could be computed as follows. NT minus KT people don't commit a crime, and they get an average score of X. So that's the total score given to them. KT people do commit a crime. They get an average score of Y, so that's the total score given to them. So the left-hand side is also the total score given out to the group. Now, by calibration, it equals KT. And now we just rearrange some terms, and we discover that X equals 1 minus Y times KT over NT minus KT. That's just a little algebra rearrangement. What does that tell us? Well, each group T gives us an equation. So we have 2 equations, one for group A, one for group B. Each of them says X is equal to 1 minus Y times something. But if the base rates are unequal, then the 2 equations are different. They correspond to lines in the xy plane with different slopes. Okay? And so the only way they can meet, the only way we can have equal averages, is at this one point, which is y equals 1, x equals 0. But y equals 1, x equals 0 says I'm perfectly predicting. I'm giving a score of 0 to the people who don't commit a crime and 1 to the people who do. Okay? So it says we really have 2 possibilities. Either these 2 lines are actually the same line, then I can do it, and I have equal base rates. Or these 2 lines are different lines, and then I can only do it when I have perfect prediction, the 2 conditions that we want. Okay? And filling in some extra details behind this, that's fundamentally how the proof is working. Okay. So there's a number of interesting questions here. One is, in the end, to think about how do we reconcile these multiple definitions of fairness. And as I said, a number of lines of work have gone on to think about how we would operate if we want to emphasize calibration, or how we'd operate if we want to emphasize balance among the averages. But fundamentally, it's saying there are reasonable definitions here that are inherently incompatible. And that's one of the hard things you would argue about trying to formalize the notion of fairness. Here we had several reasonable formulations, and we simply can't achieve them all. There are a number of other things we could talk about. It's not possible to make this impossibility go away by having some approximation. So without going into too many details, if we can achieve all three properties approximately, then in fact we either have approximately perfect prediction or approximately equal base rates. Okay. I want to talk about briefly one extra theme that's going on here, which will bring this back to some of the other applications that I considered at the beginning. So far we've talked about assigning a score to individuals, and we're really evaluating people one individual at a time. In the criminal justice context, arguably, that's what we should be doing. We should be deciding each case individually as fairly as possible. But in many of the contexts I was talking about, that's actually not what we're doing. If we're hiring, we're not necessarily hiring individuals. We're actually hiring employees at a company who will all be working together. If we're admitting students to a college class, we're not admitting individual people. We're admitting an entering class. And so often we actually want to evaluate the set that we're selecting, not just the individual. And we could ask, does that actually change things? Well, first of all, it certainly allows us to make statements that we can't make about individuals. So if I go back to my own institution, Cornell, this headline from a couple of years ago when college admissions had just been completed said, "The admitted class of 2019 is the most diverse in Cornell history." Now, that's not a statement you can make about any individual that you admitted, right? No one individual is the most diverse in history. But it's possible for the admitted class to be the most diverse in history. And if we think about goals like diversity in admissions, they only make sense if we are actually evaluating a set. There are a lot of cases where this comes up. So for example, if I'm trying to decide which loans to make, for example, you could I could ask you, is this loan a good idea? And it would be fair for you to say, it depends what other loans you're making, right? If, for example, you want to balance your risk across different categories or different scenarios, you would have to know the whole set of loans, not just one. Similarly, if we're hiring for a company, selecting a team to maximize performance may not be the same as selecting any one individual. Okay, so this point was really brought into sharp relief by a sociologist, a social scientist at the University of Michigan named Scott Page, who really pointed out that this notion of diversity and team performance is something that has to be evaluated at the level of groups, not at the level of individuals. And so I want to talk about one interesting point that comes up mathematically when we think about this question of evaluating groups. And I'll actually use a similar hiring scenario to what Professor Mathieu was talking about, although in contrast, where she was talking about selecting one person from a stream of people who arrive where you have to make decisions immediately, I'll be talking about a case where we want to select a set of k people out of n. Right? We'd like to select an admitted class for college, for example. And we're able to look at everybody in making this decision. But the challenge is, right, the challenge is not the one-pass nature from before. The challenge is, again, we can't really evaluate them fully as individuals. We have to compute some features from them and decide based on that. In particular, if we think about the college admissions situation, we're going to imagine abstractly that we give each person a standardized test, and we want to select people based on their test score. Right? This is the challenge we have. We would like to evaluate this as fully and satisfactorily as possible, but we know very little about each applicant. And so in comes a test score, and we're going to have to try deciding based on these test scores. Okay, so that's sort of the schematic. Some large universe of applicants. We're going to select a set T of k of them based on a test. Now, abstractly, we're going to model this by saying, as in the previous instances we've been talking about, that each applicant, their future performance is described by some random variable. So applicant I, random variable x sub I. We'll assume these are all independent random variables. So that means when they get to college, how they do is going to be some draw from xi, right? So each applicant shows up with, for example, imagine abstractly, some randomizing device like dice. They get to college, they roll these dice, and the numbers that come up are their performance in college. What would it mean to apply a good standardized test? Well, it should be evaluating something about their future performance. So the standardized test, F, will take this random variable xi and produce a numerical score, some number that says how they're doing. A natural first one that we might want to experiment with is the expected value of the random variable. Right? What is their average performance over all draws from this random variable? And we're going to select the k individuals with the highest test scores. So how good is the set that we select? Well, it depends on two things. One is the test. The other is actually how we evaluate sets. Right? What does it mean to select a good set? So here's a simple example. Maybe the simplest possible example would be, suppose our objective in doing college admissions is simply the sum of the performance of everybody who we admit to college, or the average performance. Okay? That would be a reasonable thing to do. Then the standardized test should just measure the expected value. And actually, it's not hard to show that choosing the k people with the highest test score optimizes this objective. So if my goal was simply a sum, then that would be fine. Now, the argument, again, beginning with the work of Scott Page, is that this is OK if, for example, we're trying to select k people to all stand next to each other and independently produce things as fast as possible. Then the total output of that group will simply be the sum of what they produce. But in many cases, that's not actually what we're looking for. If we're trying to hire a team, for example, we may want them to work together. We may want complementary skills. And so if the k highest scoring people all have exactly the same skills, that may be redundant when I should in fact find a set of people who have skills that don't overlap. Similarly, if I'm trying to admit a diverse class, then I can't evaluate that just by adding things up individually. I have to look at, did these people have different interests, different backgrounds? If, for example, I'm simply looking for a diversity at the level of academic interest, it could be the k highest scoring people all want to study exactly the same subject, whereas in fact I want a good mix of people who want to study science, humanities, art, and so forth. So there are lots of reasons why I may not be looking for the sum. Here's one that's sort of interesting to think about, and where we can get a very concrete example that I'll point to and then wrap up. And that is, suppose we're interested in the maximum performance of anyone in the group. So imagine a situation where I was selecting k people. They're each going to do something, and the success of the group is actually the success of the best one. Right? So they'll all have an idea, and we're just going to take the best idea from the group. How would we select for a team then? Okay? So we'll call this a kind of contest objective. It's the maximum of the k random variables. Okay? Maybe even, for example, I'm selecting an entering college class, and my college's reputation will be judged by the most successful person who graduates from it. Right? How would I optimize for that? So now, computing expected value can be an extremely bad idea. So suppose, for example, let's just work out this little example. I have 1,000 candidates who are what we might call high risk, high reward. They produce a value of 500 with probably 0.001, and they produce a value of 0 otherwise. I have 1,000 other applicants who are very safe. They produce a value of 1 with probability 1. Okay? So the first 1,000 have an expected performance of 0.5. The second 1,000 have an expected performance of 1. So if I have a test that evaluates the expected value, and it has to admit 1,000 people, it would admit this second group of 1,000. And if I were trying to maximize the sum, that's what I should do. But if I'm trying to maximize the best performance, then notice that if I choose all 1,000 of these, most of them will produce a value of 0. But one of them achieves a value of 500 with probably approximately 40%. We have to actually work out the arithmetic, but that's what it works out to. Basically, they have to all not fail to get 500. So with probably 40%, I get a value of 500, which means my expected value in the second case is actually 0.4 times this value of 500, or 200. I'm doing 200 times better by picking the first group than the second group if my goal is the maximum. Because with 40% chance, I get this enormous number of 500. Whereas if I pick these, I'm guaranteed to only get 1. So if I were to give people a test based on expected value and pick the highest scoring people, I'd be doing extremely badly under this goal. Okay? So what's the problem here? Are tests no good? Well, in fact, it simply says we might just have the wrong test. And so one thing that we're able to show, actually, is that even in this scenario, there actually is a test I could give people. So that if I were to rank by that test, I would be picking the right people. It's just not the expected value. Okay? Here's what the better test is. And this is in some work with Maithra Raghu. It turns out if we're trying to optimize for the maximum, then what we could do is give each applicant, evaluate them as follows. Their value is going to be the expected maximum of k independent draws from their performance. Okay, so rather than take their expected value, picture that I sampled from their distribution k times and picked the expected maximum. In other words, it's like saying to an applicant, let's think about the best case scenario. If you could live your life k times independently, what is the best you would do? We're going to have that be your score. And what we can show is that if you sort by that, then in fact we get a set that's approximately optimal, even under this maximum measure. What's interesting here is that we often think about admissions decisions for things like college or hiring as being based on potential. Right? A college admissions office will often say, we're not just looking at your past history, we're looking at your potential. And in a way, this theorem is a kind of abstract formalization of what it would mean to choose based on potential. Because it's saying, this is sort of the upside. This is, if I let you try many times, this is arguably the best you would do. And we could use that as our test. Okay? So part of the message, though, I think is less about this particular test working in this particular situation, and more about two things. One, that sometimes when you're selecting people, you're really trying to evaluate the group as a whole, using some measure that depends on the group, not just the individuals. And this notion of the maximum performance is one way that comes up. That can't be determined from any one person. It's really a function of the group. And second, that when we think of selecting people based on things like tests or numerical evaluations, there's not only one way to do that. We could admit people based on expected value. That would be good for some objectives, bad for others. But sometimes when it's bad, there's a better test that would produce better results. OK, and with that, I will just wrap up with this concluding slide. What we've been trying to think about is how to begin talking formally about some very hard to define concepts: fairness, evaluation, diversity. And what we find is that sometimes when we write these definitions down carefully, there are these inherent trade-offs between them that we didn't expect. And what that says is, clearly, we can't use an algorithm or a mathematical model to decide which definition of fairness we'd like to use as a society. That's a question that all of society has to be involved in discussing. Where the formal models come into play sometimes is, as here, to show what the limitations are in the different definitions that we're trying to achieve and what it would mean to achieve one versus another. And this second point, there are many contexts where we often take this complex data about individuals and turn that into features and assign some kind of prediction, probability estimate, or score. And how we do that can depend a lot on the objective that we're trying to achieve and whether we're evaluating people as individuals or as groups. So there are a lot of interesting questions to think about here. It's really the beginning of a line of work that's involving technical and mathematical people with people working in law, policy, the social sciences, and to some extent the humanities. And I think there's going to be a lot of opportunity for interesting work on this going forward. Thanks very much.